Hey guys, welcome back. In the previous video, I was talking about the design of a subcarrier spacing for 4G OFDM system. In this video, I will mainly focus on the design of subcarrier spacing for 5G OFDM system. Okay, so we had considered two aspects. One is the symbol duration should be far greater than the delay spread, right? This symbol duration is linked with the subcarrier spacing given by the equation 1 by delta f. So delta f is the subcarrier spacing. Okay, so this is one condition, and actually this will lead to the concept that the delta f. Okay, so delta f should be far less than the coherence bandwidth, right? Now the second concept which it is linked to is the symbol duration should not be large, should be actually much smaller than the coherence time. Okay, coherence time says this the duration which the channel is constant. So this will lead to the um, concept in the frequency domain as delta f should be greater than the delay spread. Okay, so these two conditions uh, are fine for 4G. So let's say in case of 4G we had got the delta f is equal to 15 kilohertz. We have this based on 3GPP spec, for which the symbol duration is 66.67 microseconds. Usually for the cell size considered in case of 4G, the tau d will be approximately 3 to 4 microseconds, right? So this tau symbol is far greater than tau d. This is fine, condition is satisfied. And also we had mentioned in case of 4G that we will support up to 100 kilometer per hour Doppler, 100 kilometer per hour high speed, right? So even considering this, the Doppler spread was well within the given 15 kilohertz. Now in case of 5G, we have different subcarrier spacing. We are calling it as numerology, and it is actually 15 kilohertz into 2 to the power of mu, and mu is equal to 0 comma 1 2 3, right? So basically we have 60 kilohertz, then 30 kilohertz, then 120, then 240. Okay, 240 is for a different channel and different scenario. Maybe these three were predominantly used for transmitting the data, whether it is the PUSCH data in the uplink or PDSCH data in the uplink. These terminologies will come in the future, but for now, remember that it is the data which we are transmitting. This in the uplink, this is in the downlink. Okay. So when I, let's say for example, I consider 60. Let's say I consider 30 kilowatts. What is going to happen to my symbol duration? Okay, symbol duration will become approximately, I will say approximately 35 microseconds. Okay, but what would be my tau d? Tau d is approximately 3 to 4 microseconds, right? So now let's say I'm going even 60 kilohertz. Let's say delta half is equal to 120 kilohertz. What's going to happen? Half of this 17, half of this around 8 microseconds, but this is 3 to 4 microseconds. That's why these applications are used for a different cell size. Okay, we can call it as small cell size. Small cell, for small cell applications, we see that the tau d is actually smaller. So maybe approximately this is zero point 0.5 to approximately 1 microsecond, something like that. Okay, so it is less when compared to this. This is for a macro base station or larger cell. So in case of 5G, mainly when we are using when we are using higher frequency, or I would say millimeter waves. So we have, what are the problems we have? We have high attenuation, right? The signal gets attenuated much faster. So our base stations or our cell size should be smaller. So there it makes more sense. And in a small in a small cell case, the tau d is smaller. So even if we are going to increase the delta f, that 8 microsecond is actually far greater than the tau d, and it satisfies the condition for the design of delta f. Okay, but what are the other reasons? Other reasons is that in case of 5G we want to support higher speed, the speed of a bullet train, so around 400 kilometer per hour. In this case, so definitely the Doppler spread is high, right? So let's say I will consider a subcarrier spacing or width of let's say 15 kilohertz. So for 100, let's say I will write it here. For 100 kilohertz, maybe the spread might be this much around this frequency f. But for 400 kilometer per hour, the spread is, let's say, this much. Okay, the spread actually increases, right? Doppler spread. So then definitely this 15 kilohertz will not be sufficient to cater this high Doppler spread. In this case you will have severe bit error rates. So definitely for higher speed we need a subcarrier spacing which is much larger than the Doppler spread which we are going to support. So that's why here we have even higher subcarrier spacings. Okay, so that is another reason. Then what else we have? So because in case of 5G we are going for higher frequency, right? Higher frequency means millimeter waves. What is more significant? Okay, um, phase noise will be more significant. Phase noise is actually directly related to the local oscillator frequency. Higher the frequency, higher is your phase noise. In case of 4G, the phase noise was not so predominant, and that's why the 15 kilohertz was sufficient. Even this phase noise is actually going to create some sort of a spread around this frequency f. So let me write it here. So even let's say this is the f, this phase noise is going to create a signal at some more frequencies around this frequency. Okay, all right. So now this in case of 4G, this spread was again not so significant. We were able to recover the signal, and we didn't have any kind of distortion or intercarrier interference and things like that. But moving to millimeter waves in 5G, this phase noise has become more significant, and even the spread because of this phase noise is also significant, and this 15 kilohertz will not be robust enough to actually cater the phase noise effects. So definitely in this case we need a higher subcarrier spacing. That is also one of the reasons why we had gone to higher subcarrier spacings. I hope you got the clarity. If you are looking for more videos or more concepts related to wireless communications or 4G, 5G, please do subscribe to the channel. Thank you very much. Have a great day. Bye bye.